learning projects, machine learning frameworks like PyTorch. PyTorch, I think, is #1 today. TensorFlow are recommended. Image editors, my favorite ones are GIMP and Fiji. I recommend them to everyone. If you have 3D data, for example, 3D camera, if you have a 3D camera or a LiDAR, you can use the point cloud library. And on top of all this, if you have a good algorithm, you need to deploy it. You need, almost all the time, you need to optimize it. And for this, hardware optimization libraries are needed. For example, CUDA for NVIDIA GPUs, OpenCL for basically everything else. And the good thing is they have bindings in Python, so you can model them in Python and test it before deployment. Okay, let's start with detection of simple shapes and patterns, like 50 years ago. So why do we need detection of shapes and patterns when we can recognize pedestrians and cats and dogs and everything? One particular use case is camera calibration. So basically, there is no single two identical camera in the world. I'm talking about cheap cameras that everyone is using, for example, in the mobile phones. Each and every camera is different. It's usually because their optical system is a little bit different. So here's a simple pinhole camera model. This is, for example, one camera, but in the other, the lens parameters will be a little bit different. In another one, again. So we will have different lens parameters, and it will result in that the sensor array that you can see here, that is basically taking the picture, the image will be in different parts of the sensor array, depending on the optical properties. Now, this is not a problem if you are taking an image with your phone, because you see it on your screen, and you see it on the screen what you are taking. But if it's on a robot or on a car, that becomes a problem, because you want to find the real world position of the object that you find on the camera. So if you fix your image and try to find this object in real space, and the camera parameters change, then you have a problem, because you will think that that object is somewhere else. For robots, this particular calibration is called hand-eye calibration, and apart from the optical properties, another parameters must also be established. So here we see a robotic arm. This is the tool center point. This is a reference point for the robot where we attach the tools, for example, the grippers. The robot knows this position very well in space, the orientation and the position, hundredths of a millimeter precisely. However, the robot doesn't know where the camera is looking. The camera has its own coordinate system. We have to find the parameters that translate from camera coordinate system to robot coordinate system. This is the camera matrix equation. Not really important. This is the image coordinates, and these are the real world coordinates. And these are the parameters that we need to find. Oh, these are the optical parameters here, and these are the external, the rotation and translation parameters. How it's done? There are many methods to how to do it. One preferred method is that we have chessboards. Basically, we let the robot, the camera on the robot, see these chessboards from different angles. We know the coordinates of the chessboard corners properly. Then we detect it with the camera. We use OpenCV to detect the chessboard corners, and then we can solve this equation, or use an optimizer to solve this equation, so that the checkerboard that we see on the camera matches the real world position that we know. So I have a video about how it looks like in practice. So this is an industrial robot. It's in a cage because it can be dangerous. Here the camera really. Here the camera is installed on the robot. Here down is the checkerboard, and this display sees what the camera sees. After detecting the corners, unfortunately it cannot be seen here. Detecting the corner, the computer will calculate the camera matrix parameter and write it on the camera flash. This camera is ready for packaging. This is pretty this is very good. This hand-eye calibration has very good support in OpenCV. However, there are things that are not so well supported in OpenCV. Anyone have a guess what we can see here? Circles. Yes, circles. Oh, sorry, I should have started the video. So basically, these are ball bearings. These are ball bearings, and in an X-ray image. And these ball bearings are used to calibrate a CT machine. So this is like a schematic of a CT machine. It's an industrial machine used to study materials. We have an X-ray source here, and we have a detector that is like a camera for X-rays. And we have a sample here that is turning a full circle. A lot of images are taken on this detector, and with an algorithm, the many 2D images are made into a 3D image. The same thing happens in the hospital for clinical CTs. The difference is that in the hospital, it's not the patient who is turning around, but the X-ray source and the detector is turning around in a ring. Okay, so in order to have precise reconstruction, 3D reconstruction, we need to know several parameters. For example, the distance of the X-ray source and the rotational axis. Also, how the detector is aligned with the rotational axis. It's usually it's rotated a little bit, tilted, and so on. So we measure the properties of these ball bearings, and calculate with a model from a few starting parameters how, if we so we basically model how they should be on the X-ray detector, and then we again, same with the camera calibration, we optimize the model parameters. And there's a problem though. For circle detection, OpenCV has this Hough transform. Basically, it works by using image gradients. Image gradients, I think it may be worth to speak a little bit about them. So image gradients are showing the dominant change at a particular in the neighborhood of a particular pixel. So basically, how we calculate it, for each pixel we subtract the upper one and the lower one. This is the vertical gradients, and we subtract also the left one and the right one. So we get a full gradient for each pixel. As you can see, the gradient is a vector. Its length is the biggest when there is an edge. So it's very good for edge detection, and also it's perpendicular to the edges. Hough transform uses this property. They elongate the gradients, and where the lines, the elongated gradients intercept each other, there you find the center of the circle, and then you can easily find a whole circle. The problem with that is that it is a local search. It always uses only a few of the points because of numerical errors and noise causes the algorithm to have many centers. So it works by voting, and the result is usually something like this. If you look at it, it's not very precise. If you want to calibrate with this, it won't work. You will get a blurry 3D reconstruction. So we need to correct for it. How do we correct for it? We create a score. Basically, we multiply the circle that we detected. We multiply the gradients of our own circle and with the image gradients, and we get a score. When the video started, the score was like 45%. Now you can see it aligns much nicer to the actual detected circle. It goes up to, I think, 70%. So it gives us a much more precise readout. Okay, so this is for shapes. Let's go for another example. Detection of rigid objects. This is actually this project was a use case for small and medium enterprises who are doing manufacturing, who have a small workshop, maybe have a CNC machine and want to use robotic arm to pick the machine parts and feed it to the CNC machine. So this is very much different from what we saw before with neural networks, detecting a cat or a dog. You can detect any cat or any dog. Here we have to precisely detect the machine part that we want to pick. And not only that, we need to find the exact orientation because the robot must grip it always at the same position so that it can be put into the CNC machine. Usually in a factory floor, we don't usually have connectivity to the internet. Also, we cannot expect to have GPU farms that can train us and run neural networks. So we have limited hardware, and also the users want pretty good recall. They want us to recognize every single item and pick it, because if you don't pick it, they have to put a man there, and then this man could basically replace the robot. They could obsolete the robot, because if there is already someone there, then he could load it at that way. Okay, it's not as easy as it looks. So how to do it? First thing, let's use state-of-the-art neural networks. There are some problems with neural networks. We need to train, because these machine parts, they are not like cats and dogs that they are always the same. These machine parts are very different. All has a different shape, and each of them has a different shape. And we will need to train a neural network for each of them. This takes a lot of time and money. Also, neural networks, you have to show a lot of pictures. In a factory setting, it doesn't work. They want to change 3 times a day different machine parts. They don't have time to train neural networks and annotate them and so on. We don't have good hardware, and maybe it's interesting to see that neural networks are not really good by default to find the orientation of an object. This is a quite good neural network. It was a leader in ImageNet. But as you see, this fur coat is turning, and while it's in a normal position, it can recognize that it's a fur coat, but then it says it's a broom, it's a towel, whatever. So unless you train the neural network properly, it will not recognize well rotated objects. Of course, if the neural network is shown all these rotations and trained for it, then it will recognize it properly. Okay, but usually it's not done this way. Okay. Another thing, background subtraction, very easy. Take a picture of the background, then take a picture of your object, subtract the values, find the contour of the object. That's the teaching process. Then you can relatively easily find these screws based on this, because the length of the contour, the area of the contour gives you a good guess. You can exclude these 2 parts, for example. You get a localization. So it works for the very primitive use cases. However, it has limitations. For example, if you put 2 screws together, two parts together, which is quite common, then it stops working. And also, if the light condition changes just a little bit, then you have a problem, because the background subtraction doesn't work anymore. No wonder it was neglected in the early 2000s. What other we have, which is not neural network? Feature points. Feature points, basically these are mathematical structures that find on an image landmark points that are really special, and they can match these points on another image. It works pretty well for example, buildings, and also I heard this works pretty well for the night sky. Astronomers use it to compensate for the rotation of the Earth. But if we use it for machine part, it really works very badly. For example, it matches this point to here, whereas it should be here. So basically, it cannot really find a match. It's totally useless for our purpose. So what is the solution? We go back to the gradients again. There are good algorithms based on gradient match. The way it works is that with background subtraction, we teach the algorithm with the background subtraction, basically show it the background and the image. We got our query object. We want to get this object. We take the edges and gradients, and then we start looking for these gradients on the image in a downsampled low resolution image. And when we find a match, we go into higher resolutions, do some refinements, If it's still good, we do some more, and if it works on the highest resolution, then it's a match. It finds many false positives, so many objects that are not really there, and low resolution. But as we zoom into the image, higher resolution, it no longer matches. The score stays low, and it's discarded. This algorithm is very easy to parallelize. For an image like this, it costs about 100 million instruction for image. That means it can run on a CPU. We don't need GPU for this, and as you can see, it works pretty well. And also, it not only works in the computer, it works in real life as well. As you can see, so this was the very first time it started working. So there's a cube in my hand, and the camera on the robotic arm can recognize the cube in my hand. This is a pretty hard task because my hand is about the same color as the wooden cube, so it is really hard to see. Really hard to see for the algorithm the cube, but this also proves the power of the gradient-based algorithms. Okay, non-rigid object detections, detecting, okay, back to cats, dogs, humans, cars, whatsoever. This was a project. This was a rear view camera on a car, and here the goal was we had a fisheye camera, a wide-angle camera, as you can see here from the distortion, and here the goal was to detect a few objects of interest: humans, baby strollers, cars, bicycles, motorcycles, whatsoever. There were very strict requirements for the detection of humans in the vicinity of the car, and so basically all this is not a big deal this time. Like actually, it was about 4 years ago, but even that time it was not a big deal because you could download from the internet networks, ready-made networks that can do just that. However, the trick was that we had a very low computational budget. We had a specialized chip which had about a 2 watt power budget. In comparison, a GPU, which is many times used for training and running neural networks, is 250 watts, 10 on the 12th power instruction per second. This very specialized chip had 80 billion operations per second, and there was a requirement that it has to be running at the 20 FPS, so that the user at the dashboard of the car sees a moving picture and sees the boxes moving, not behind the human, but together with it. And there were also prices for this small chip. For example, there were limitations that the chip could only run one type of convolutions. So for this purpose, of course, we used convolutional neural networks. A few words about convolutional neural networks. As I said, they exploded around 2012, about 10 years ago. They exploded to the scene. There is a relatively known challenge, ImageNet, where you have to classify images into 1,000 different categories. Anyone can basically participate in this challenge with these algorithms. It started, the last version started in about 2010, and then the dominant algorithms were the feature point based algorithms, which were about 50, which could classify properly about 50% of the images. Then the first convolutional neural network of this size, the AlexNet, came in 2012, and it went already up to like 70%. And then up until this day, a few years ago, about 90% accuracy was achieved. And quite recently, about a year ago, interestingly, the transformer-based networks took over the original convolutional network, the ChatGPT-like networks. It's pretty interesting. This is how a convolutional neural networks looks like. We have the input colored image. It has 3 channels, red, green, and blue. and we create from it other multi-layer images. We run a convolutional filter through the image and create a many-layer image. These are usually like 50, 60, 100 layers deep. They occupy a lot of memory and a crazy amount of computation, because the way to calculate how much computation is needed is that you need to multiply the filter kernel size, which is like 9 or 25, to the number of input channels with the number of output channels and the number of output dimensions. It's billions of operations. And we have a lot of such layers, and we have some different types of layers like branching. We have nonlinear layers, and at the end of the convolutional networks, this one is a classifying network, so it has a softmax output. It gives us one probability basically for each category, so each of the 1,000 categories. But for object detection, it's a little bit different. We have this convolutional network layer that creates these feature heat maps. Then we go back in a feature pyramidal network, it's called, create more features, and then we have detector heat maps. These detector heat maps usually consist of like one grayscale layer that tells you for every pixel, is it an object or not. We have several layers like red, green, blue, but not colors, but is it a cat or dog or human? And we have like 4 layers to tell what is the boundary of this object, so that we can draw a box around it. Okay, so here, as I said, we could not download a network from the internet. We had to train it ourselves. What was important? Important was to gather enough data, enough training data. We had about 15,000 images. They were taken on various roads of various cities. Then they needed to be annotated by hand, because these neural networks, we have to show the actual ground truth and then optimize them so that they would show that by themselves. We tried mixing with different domains. We tried to use simulators. This didn't really help. We also tried to use pre-trained networks that can be downloaded from the net, but also didn't really help. What is important in training neural network? Consistency is very important. It's the same for like raising children. You have to be very consistent. It's important that whenever you show a training image for the network, you have to label it properly. If you miss out a car here, if you miss out a pedestrian there, it will ruin the training. Also, it was important to make it easy for the network to learn. That means we used a little bit different detector head. We used a bounding box predictor for each and every class. We had a very few classes. Usually the public networks, they are prepared for these challenges like ImageNet or Coco. They have a lot of classes. They have to detect every single thing in the world. We only had to detect the few interesting things on the street, like humans and cars and bicycles. So we could allow to kind of relax this training procedure. Yeah. And there was another problem, the optimization, because we had a very low computational budget. So for this, we tried different things. Downsampling the 1 megapixel image to VGA. It was good. The only problem was that the far away objects that are smaller on the image, they were not detected anymore. So we could not go down lower than the VGA resolution, where the image is like half of the megapixel image, quarter of the megapixel image, sorry, half side by side. Then there are 2 published methods for kind of optimizing neural network. One is pruning, the other is distillation. Pruning means basically cutting off the branches of a tree. You train a big network, you see it works, then you throw away layers from it and retrain it and see if it still works or not. we actually use this method. We could pretty much compress our neural network. And there is another interesting method called distillation. This is very interesting. You train first a big neural network, and the big neural network you train with absolute ground truth. You know that on this image here, this is a human for sure. So you say it's 100% human. The neural network, the big neural network, when you run it against this picture, will say this is 80%, 85%. It is a human. And when you train the small neural network, you use these probabilities taken from the big neural network, and this makes it, for some reason, this makes it easier for the small network to learn. Okay, another thing to play with numerical precision. When you train a neural network, it's usually always floating number representation, but when you are doing the inference, when you are running it on a deployed hardware, you can go down to 16-bit integer or 8-bit integer. This makes things much faster because you need to move less data from the outside memory. And also on the silicon, you can do much more calculations with 8-bit or 16-bit numbers than with 32-bit numbers. These percentages in the parentheses are how much accuracy we lose. We found that going down to 16-bit doesn't really matter, but going down to 8-bit, actually it's painful. We lose 3-4% of the detected objects. Offloading to CPU means that we had a specialized neural network accelerator that could only do one thing. And there were many different layers that we could offload to CPU. There are, for almost every modern CPU architectures, there are SIMD operations like single instruction multiple data, vector operations. Using this, we can make it faster. And basically the final network, it was like 4 billion operations per image. It was about the same size as MobileNet V2, which was like the top small network at that time. But MobileNet V2 used this trick with the separable convolution, which we could not do on our hardware. So I think that ours was better. As a comparison, the state of the art at that time, ResNet 50 was like 8 or 10 times bigger. Okay, so I hope you enjoy the presentations, and if you have any questions, please do not hesitate to ask.
I have one.
Yeah.
Back in the RoboStar experiment, So back in the RoboStar experiment, when you had the localization with the trial and you had the cuboid in your hand, so first localization is done, and after that you can't move actually the cuboid because it doesn't localize it?
Yeah, basically the localization is just one picture. When the robot goes to the upper position, I think we can go back to this video. Sorry. Okay, so the robot goes to one set position here, takes one picture and does everything, and then it moves. And whatever I do in between doesn't matter because it is not watching it. So basically everything is done according to one picture. Yeah.
The second question is regarding quantization or numerical precision. Mm-hmm. So you said this was done 4 years ago, the project training the neural networks. Mm-hmm. And back then, what type of quantization methods have you used?
Yeah, basically, I think we just cut the weights. I think, or no, I think we used the TensorFlow Lite, and it had the built-in quantization, so we don't really have to care about the quantization. It did it automatically.
Thank you.
Hi. Thanks for the presentation. I have 2 questions. One is who annotated your images, Like, did you use like Microsoft or something online?
Basically, it was in-house student workers.
Okay. The other thing is that why don't you use transfer learning? So you told there like pre-training nets couldn't be used, but I think the Coco has these categories like car and person and so on. So you could just omit the other categories and probably fine tune the layer.
We tried it, but we found that basically, I think very likely the problem was too easy, so we couldn't really get much extra from it than just training from scratch. Yeah,
Okay.
that is my theory at least. That the problem is too easy. The streets are always the same. Anywhere you go, the humans are the same. Yeah.
Yeah. And did you achieve your goal?
Yes.
I also have some questions. The first is regarding to calibration projects. Why don't you, or have you tried to move the calibration table instead of the camera?
It was easier to move the robot arm because that knows the robot knows its position very precisely. So.
And finally, you had to calibrate multiple cameras.
Yes. That's the point. Yeah. Well, not multiple cameras at once, but so the cameras were used singularly. They were used alone. So you didn't need to calibrate one camera to the other one, only to the robot coordinate system.
But my main idea was if you want to calibrate multiple cameras simultaneously, just need to check.
Yeah. Of course, that's a different issue.
Yeah. So second is the same sort of this robotic hand project. So was that somehow 3D or rotation invariant after all? Or because you mentioned it was rotation correct and you created this algorithm, but if you move somehow sideways?
You mean tilting?
Yes.
It could tolerate tilting up to 5–10%. Yeah, so this was really like for table picking.
The second was you mentioned somehow you rectificate the original fisheye image. Was it a problem on the pixel distribution that you handled somehow later?
No, not that I'm aware of. We just use the camera libraries. And, yeah.
Okay. What kind of accelerators you used for neural networks, which are included, if you can?
Unfortunately, that I cannot disclose it. I signed the NDA, so yeah.
Yeah, no problem.
You may guess it if you work in automotive. Yeah.
Have you needed to validate any neural network in any of the project?
Yes, of course. All the time. So we had test data, and also customer tested it. Like, for example, they tested it with not real humans, but like tables, dark background, dark clouded children's size puppets, and then white background, white clouded children puppets, and that kind of stuff. Yeah.
The next question is similar. So, did you use any optimization tool for neural network?
Optimization, basically the pruning like approach. Yeah.
So you use the toolset or toolbox by yourself. You just created the function.
Yeah, basically it was like handcrafted kind of pruning the layers, basically. Yeah.
One last time. Okay, so how do you handle the kind of synchronization between CPU and GPU when you did this offloading?
In the embedded accelerator.
Yes.
I don't remember this. This was the offloading kind of stuff. The CPU was running on threads, and there were some very primitive way of synchronization. There was double buffer, and the narrator was working on the image. When it finished, it passed it back to the CPU. They worked from a common memory, so you didn't need to copy it. For example, like in GP, distinct GPUs, they use the same address space. So basically, that's it. A very primitive way of passing it, like semaphore or whatever. Just the ptrace library and
That's a common memory.
Shared memory, like
Thanks.
More questions?
Okay.
Thank
Thank you very much.
And thank you everyone who joined us online, because we are now stopping the streaming. I think I might ask some help from Jennifer, if you can do that. I can do that. Okay, so thank you everyone for joining us online. Thank you, bye.